Okay, this is second hour of Physics 1C for May 4th. And we just described the phenomenon of electromagnetic induction. We wrote down Faraday's law. Can't really derive this. And now we're going to look at an application. We're going to look at this problem right here. Let's see how we actually do calculations with this. Okay, so this problem is called, it's from your textbook. It's called EMF and Current Induced in Loop. It says the magnetic field, you can hear me okay, right?
Yeah.
Okay.
Yeah, we can.
All right. Magnetic field between the poles of an electromagnet is shown there. It's uniform at any time, but its magnitude is increasing at a rate of 0.02 teslas per second. The area of the conducting loop, so here's our conducting loop right here. It's hooked up to, I guess this is a ammeter.
Voltmeter?
It's either voltmeter or ammeter. It doesn't really say, it just says a meter. But it says the total resistance of this circuit plus the meter is 5 ohms. It says the area of the loop is 120 centimeters squared, and the total circuit resistance, including the meter, is 5 ohms. We want to find the induced EMF and the induced current in the circuit. If the loop is replaced by one made of an insulator, what effect does this have on the induced EMF and the induced current? Okay, this is a pretty decent problem. It hits upon quite a few ideas. Now, what's going on with this coil? Is it just levitating in midair? Is that what's going on? Looks like it is. Okay. Anyway, so I guess this would still work even if the coil was just laying on the bottom surface of the magnet, so I guess that's fine. All right, let's write down the information we have. I guess it's all really kind of shown here. So we have a resistance of our circuit, R, that is 5 ohms. We have a magnetic field that's changing, and they tell us the rate at which it's changing, dV dt. And that's 0.02 Tesla per second. We know the area of the loop is 120 centimeters squared. We'll have to convert that to meters squared. I guess we could go ahead and do that right now by multiplying by 100 centimeters under 1 meter and then squaring it, which means this is going to move the decimal place back 4 places. So I think this will be 0.012 meters squared. If you all could check that and tell me if that's right or wrong.
That's right.
It looks like there's only one turn in the coil here, so I'm just going to go ahead and say N is equal to 1. That's all the information we have. So we want to find, in part A, we're supposed to find what is the induced EMF in our coil. And we'd also like to know what the current flowing through the coil is. So I'll write that as I with the subscript I and D. Induced current. And then we'll do part B. Okay, so to find the induced EMF, we are going to use Faraday's law. The induced EMF is equal to negative capital N d phi b dt. And moving downwards, so our induced EMF in this case should be equal to negative. I'll just go ahead and put a 1 in for the N. Then I'll write ddt right here. And then for the flux, see it says that, what does it say it? The magnetic field between the poles of the electromagnet is uniform at any time, but its magnitude is increasing. So I'm just going to write for my flux inside of here, and you'll find that this is going to be what you do for the vast majority of the problems, except for probably one of the lab manual problems. I'm just going to write it like this. So flux, right, I have this written above, but I'll just rewrite it again, is basically, it's this integral, right? But the thing is that if the magnetic field is uniform at any time, then this integral basically just becomes BA cos theta, basically, right? So where theta is the angle between B and A. So anyway, that's what you're going to use most of the time. So for using Faraday's law, it's pretty safe to just go ahead and replace the flux with BA cos theta. All right? And then we look at this derivative here and we think about what's happening. And we ask ourselves, are any of the things inside of this changing? And I guess one thing we didn't figure out is what is theta. So theta is going to be the angle between the magnetic field and the area vector. So the area vector we can see is pointing up this way. The magnetic field is also pointing up. That means the angle between the two of them is going to be 0. So that's going to be 1. And we can pull the area out of this because the area of our loop isn't changing in this problem, although it will change in some other problems. So I'll have a negative area, and then we just have dB dt right here. And that's it. We're done, basically. We just plug in numbers. So the induced EMF is going to be equal to area, which was 0.012 meters squared. And dB dt, the rate at which the magnetic field was changing, is 0.02 teslas per second. So we get an EMF that's induced in the wire of, it looks like 2.4 times 10 to the negative, let's see.
Negative 4.
Negative
4.
Yeah. Yeah. Now, the units for this are Tesla meters squared divided by seconds, which, believe it or not, that is a volt. That is a volt.
Shouldn't it be negative as well?
Oh, yeah. Yeah, negative. We'll talk about what this negative means. Did they actually do it right in the problem? Let's see. The current's increasing, right? Yeah, they did it right. So this is the direction of the current, and we're just... Don't worry about that for now, and don't worry about this negative sign for now. Just ignore that for now. But do we have to completely ignore it? It is kind of... So do this for me as a way to kind of set up what's going to come next where we understand more about the negative sign. Take your thumb and point it in the direction of the magnetic field, okay? So the magnetic field's going up, right? This has to be your right hand, as usual. If you wrap your fingers around, that's normally the direction the current goes. If you have a magnetic field. But can you see that the current's flowing opposite the direction your hand would normally rotate? In the picture?
Yeah, is this where the negative sign comes into play?
Yeah, that's the negative sign. That's exactly the negative sign. So if you were to point your fingers in the direction of the magnetic field and swing your fingers around, you should all be able to see that your hand is basically going opposite the direction of this current right here, right? And that's what the negative sign does, is it flips the direction of the current. Okay? Does that make any sense?
Yep.
Mm-hmm.
What would happen if the current was decreasing at a rate of 0.02 Tesla per second? Then this would be negative, right? And the answer would have been positive. So that's actually what the negative sign tells you. It tells you that if the current's decreasing, your answer is positive, but if the current's increasing, your answer is negative. So if the current was decreasing, if the magnetic field was decreasing, then the current would be flowing in the opposite direction. Does that make sense? We're going to go into more detail about that here in a second. We'll talk about what's called Lenz's law. But okay, so this is the answer for this problem for the induced EMF. Let's go ahead and look at the unit really quickly right here. So a Tesla meter squared per second is the same thing as, so a Tesla is a Newton meter divided by amps, I think? No. It's Newton per amp meter. The meter goes in the denominator. Okay. So that times meters squared over seconds. Amp second is coulomb. Meter over meter is meter. So you're left with Newton meters in the numerator, which is what? That's joules, right? And in the denominator, you have amps times seconds, which is coulombs. and this is a volt. So our induced EMF is negative 2.4 times 10 to the minus 4 volts, or 0.24 millivolts. Tesla meter squared over second is a volt. This is another way to remember what the connection between like Teslas and volts is, because, well, just if you look at Faraday's law, volts on this side, and then this is going to be Tesla meters squared per second on this side because of the what's in here. So, you can see that those two are the same thing. Flux per second is volts. Isn't that interesting? Magnetic flux per second is volts. It's the same thing.
Like how quickly a field is passing through an area?
Yeah, exactly. How big the field is, right? That's T. And not just the field, but the flux, because you have to take T times the area. And then it's like the rate at which that thing is changing. That's the per second part, right? That controls how big voltage is. And that's what we saw, right, when we did the, air quote experiment here, where we looked at the brightness of the bulb with low frequency, saw that it was kind of dim, and then with high frequency it goes way up. That's the per second part. The Tesla part is the magnetic fields. The meter squared part is the size of the loop. And all of those things combine together to give you voltage. In a very real way, they all combine together to give you the power that you're using to watch this stream right now. Because that's how we produce most power in the United States. All power? Probably all power. Okay, so that's the induced EMF. And now I want to find the next part of this, which was find the induced EMF and the induced current. How do I find the induced current? I always remember this seeming kind of tricky when I first started learning this stuff too. So if I know the induced EMF, which is really just voltage, right? How do I get from voltage to...
resistance.
Yeah, resistance, right? What do? Do I multiply by resistance? Do I raise it to the resistance power? What do I do?
Divide by resistance, right? To get I.
Exactly. If I take EMF over R, I will get current. So we just take negative 2.4 times 10 to the minus 4 volts and divide by the resistance, which was 5 ohms. Okay. So this is like multiplying by 10 and divided by 2. So it's going to be like 24 divided by 2 is 12. 12 times 10 to the negative 4 is 1.2 times 10 to the negative 3, I think. So it's going to be something like 1.2 milliamps. Is that what it is?
Getting 4.8 to negative 5.
Ah, okay. Well,
Negative, yeah.
that makes sense. Yeah, it shouldn't get bigger, right? No, it's not times 10 over 2. It's times 2 over 10. Oops. Okay, so it would be, 4.8, and then divide by 10, so it's going to be, 4.8 times 10 to the minus 5 amps. Is that what you got?
Yeah.
Pretty simple Faraday's law problem. We'll see more of these, and they can get kind of tricky, but this is, it's the basic concept of what you're going to be doing when you solve these kind of problems. So, does anyone have any questions? Okay. So, the next thing to do, I think we want to talk about Lenz's law now, because I don't want to keep. That has to be the next thing, right? Yeah. Okay. Lenz's law. All right. So let's grab this. We'll leave these for a second. We're just going to grab this one. Okay, so Lenz's law describes what the negative sign in Faraday's law means. And it basically states that the direction of the induced EMF will be such to oppose the change of magnetic field flux. That's pretty much what it says. Okay, I'm going to write the short version, and then we're going to write the version that's actually easy to understand. So the direction of induced EMF opposes the change in flux. I think that's like the least number of words you can use. I could also write an entire paragraph for Lenz's law, but I think this is good enough as a starting point, and then we can go into more detail about what it means. But this is a little easier to remember. The direction of the induced EMF opposes the change in flux. So what does that mean? That means that when the flux is increasing, the induced EMF has to be opposite to the external magnetic field. And when the flux is decreasing, the induced EMF is going to point in the same direction as the magnetic field. Does that make sense? I'll write down what I just said.
So is the direction like high to low voltage?
Kind of. I mean, I think about it in terms of the direction of the field, the magnetic field. This is 1/2 of what I said in the law. I'm just trying to like write it out in words, and then I'll show you in a picture. When the flux through a loop is increasing, the magnetic field produced by the induced EMF is opposite to the external magnetic field. That's not how you spell magnetic. That's how you spell, like, not a word. Okay. So let me see if I can draw a simple picture of this before I go to the pictures that come out of the textbook, because they're kind of busy. So let's say that I have a magnetic field that points this way, okay? And I'm going to define that it's the external magnetic field to be very clear about what's going on. So this is my external magnetic field. And let's say that this is increasing in time. Okay, so the external magnetic field is increasing in time, okay? And that's what that subscript means. BXT is external. Now, around this object, I place a loop of wire. And my loop of wire is going to come around like this, go around the front of my magnetic fields, and then come back around this way here, okay? So here's a loop. It's just a loop. It doesn't have any whatever. And it connects on the back side, but I just want to make it look like this is the front and this is the back, because it can be kind of hard to tell sometimes with these pictures, okay? Okay, so here's how this works. So if I have an external magnetic field that's increasing, according to Faraday's law, there is going to be an EMF induced in this loop. Would you all agree?
Yes.
Mm-hmm.
Okay, so the question is, what direction does it point? Okay, and the best way to ask that question is, if I look at the front here, is the current going this way or is it going this way, basically? Those are my two options, right? The good thing about Lenz's law is it's kind of complicated, but there's really only two options. So if you get it wrong, it's the other one. You know what I mean? So the current that's induced is either going to go to the right in the front or it's going to go to the left. Okay? Now let's look at what this states right here. let me erase these arrows too. I don't want to be too confusing. We know there's current. We just don't know what way it goes now, right? Okay, so this is what it says. When the flux through the loop is increasing, okay, check. That's what's happening here. Flux is increasing because the field is increasing in this case. The magnetic field produced by the induced EMF. Okay, so there's going to be an induced current, and that induced current has a magnetic field, right? Because we learned that if you have a loop of wire, right? If I have a loop of wire, and if this is the front, so we'll just put the word front on here so it's really clear, and this is the back over here, so this is coming kind of out of the screen, what's the direction of the magnetic field that's produced by this wire right here if there's current flowing like this?
Up.
Up, exactly. So the magnetic field in this case would point up, okay? So we need to make it so that the current that flows right here produces a magnetic field that does what? It has to be opposite to the external magnetic field.
Has to be going clockwise.
To be going down.
Yeah, so that means, and let's put another magnetic field on here now, because I think this is the order in which you should do it. You should say, take your thumb and point it in the direction of the external magnetic field. If the magnetic field is increasing, you need to turn your thumb upside down, and that's the direction of the induced magnetic field. So I'm going to draw on the same picture right here, there's going to be an induced magnetic field that's going to go down. I'm going to call it the induced magnetic field. So B with an IND subscript. So magnetic field induced is this way. And when you know what direction the induced magnetic field is, you can now go back and figure out the direction of the induced current. So what direction does the induced current need to be such that it produces an induced magnetic field that goes down?
Clockwise.
The
Clockwise.
clock.
Is that left or right on the front right here?
Oh,
That's
left.
Left.
Okay, yeah. Because clockwise depends if you're looking from the bottom or the top, right?
That's true.
Gotta be kind of careful. So that's the direction of our induced current now. Okay, did you all follow that? Did that make sense?
Yep.
Yep.
Okay. So now that you know that rule, that's what happens when it's increasing. When it's decreasing, it's just the opposite. The induced magnetic field will go up. Okay? So I'll write that out in words. But this is the increasing case. Right? The decreasing case is 100% the opposite, right? In fact, I'm not going to do it. I was going to use the same picture. So let's do the decreasing case, okay? The decreasing case is, okay, external magnetic field points this way. I put a loop around it. There's my loop. And now I tell you that the external magnetic field is decreasing in time. And so I say, okay, because the external magnetic field is decreasing in time, my induced magnetic field needs to go in the same direction. And that means that the induced current that will produce such an induced field has to go this way. That make sense?
Yep.
And that covers all the possibilities. Now it's going to get a little more complicated when we actually use real magnets, but we're going to look at a few different things. So I will write out the other half of this, which is, when flux through a loop is decreasing. And now that I've actually gone through some of this, I can use some of this language. The induced magnetic field is in the same direction as the external field. And then you just go from there. If you can figure out what direction the induced field is, you should be able to use the right-hand rule to figure out the direction of the current, right? Yeah. So my rule for how you go through this process, I'm not going to write this out, but this is the procedure that I go through when I don't know how to solve a problem. I start off by looking at the external magnetic field. Okay, so let's just look at the one that's up here at the top. And I say, point my thumb in the direction of the external magnetic field. And then I say, is the field increasing or decreasing? When it's increasing, I turn my thumb upside down. That's the induced field. When it's decreasing, I leave my thumb in the same direction. That's the induced field. And that's Lenz's law. So, having said all of that, can you see how that's basically summarized by this? When flux increases, the induced EMF is opposite. When flux decreases, the induced EMF is in the same direction. And a simple way of stating that mathematically is just a negative sign, right?
Mm-hmm, mm-hmm.
When d phi dt is positive, you get a negative sign here. When d phi dt is negative, 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 you get a positive sign. That's how it works. And that's what the negative sign means. Now, after having said all of that stuff, that means that you don't really need to use the negative sign if you don't want to, right? Because, it's just like gravity. When we talk about gravity in Physics 1a, you can either say the acceleration due to gravity is negative 9.8 meters per second squared, by which you're kind of implying that you mean that down is negative, right? Or you can just say g is equal to 9.8 meters per second squared, right? At the end of the day, it means the same thing. We know gravity goes down. Do you really need to throw a negative sign in front of it? Or can we just incorporate that into all the problems that we do, which is what we do in Physics 1a, right? Like, we don't just automatically make g negative in every single problem. We use our brains, and we use vectors, and we draw things. And we like, okay, in this case, the weight is actually down, but you're on a ramp, and so that kind of changes how gravity works a little bit, right? So I feel the same way about this negative sign. I don't really like to write it all the time. So a lot of times what I'll do is I'll just write absolute value sign over here when I don't care about it. Because what we're going to do is we're going to use Lenz's law as our way of figuring out directions of currents, basically, right? And we use Faraday's law to figure out the magnitude of the currents. That's the way I think about it, at least. Lenz's law for direction, Faraday's law for the magnitude. Okay? Anyone have any questions before we start looking at some examples where I kind of challenge you to try to figure this out yourself? So we'll do these ones, but I think I have some simpler ones. I don't know if I copy-pasted them over. Okay, so I grabbed an example from another textbook here. Get this. So if we go back here, I messed up all my notes by, where's the, this one right here. Okay, let's look at this example. Okay, I cannot promise this is going to be simple. The first few of these that you do can be quite complicated. But I'm going to read this, and I'm going to have you all, like, kind of, maybe if you have a piece of paper or something, like, write down your answers, and then we'll compare answers, okay? So it says, use Lenz's law to answer the following questions concerning the direction of induced currents. Express your answers in terms of the letter labels A and B in each part of the figure. So you have A and B. So the current's either going to, for example, for part A, it's either going to flow from A to B or from B to A. Same thing here and here. Okay. Okay, part A says, what is the direction of the induced current in the resistor when the bar magnet is moved to the left? Okay. Now for bar magnets, I'm just going to mention, to make your lives a little simpler here, you can basically treat them as like a little B field if you just say, make the magnetic field basically just point this way. I'm not going to do a good job of drawing this straight, but I'll try. You basically just say that's the direction of the magnetic field, okay? That way. The green's not really showing up very well, but to the right, okay? So it's north-south, but I'll write this over here because it's probably easy. So if I have a north-south magnet like this, then you basically just treat it as if there's a magnetic field that basically goes like this, okay? It's the easiest thing to do. Yeah, I mean, it also loops around and stuff, but you don't really need to worry about that too much. The strongest part of the field points like this. Okay, so here's a magnetic field, and it's going away. Part B says, what is the direction of the current induced in the resistor immediately after the switch is closed? Okay, so for this one, this is kind of tricky because now you have an electromagnet because you have a coil of wire and you've got a battery. So the question is, when you close the switch, there's going to be a change in flux through this loop, and you want to find the direction of that current. And then finally, part C, what is the direction of the induced current in the resistor when the current I decreases rapidly to 0? So again, there's no magnet here, but we know that magnetic fields are produced by current carrying wires. So you need to, there's a lot of right-hand rule stuff you have to do here, but I want you to take like 5 minutes. I don't know how long it will take. And try to solve each of these yourselves. Now, normally what would happen if we were in class is I would actually give you a big worksheet full of examples. And we may look at that worksheet. I think it's posted on the website if you want to check it out yourself. But the main thing is it would allow you to talk to each other. So if you really want to during this time, go talk to somebody else and you want to work with somebody else, you're welcome to go use all the office hours channels. You can talk to each other in this channel if you want to, for all I care. It's fine. So, yeah. If you want to do that, you can. But take like 5 minutes. What time is it right now? It is 4:13. So at like 4:18, I will start again, basically. We'll do 6 minutes. I don't know how long it's going to take you. Oh my god, you can't actually see the problems. I'm so sorry. Here we go. There's the problems. Let me know if you have any questions. Oh, let me throw one other thing on here. Where is it? Can't find it. Oh, well, that's fine.
Y'all get it, or is y'all still working on it?
They have a little bit of time left. We'll go through all these one by one. And then we'll look at more. Okay. Oh my god. Is that loud? Could you guys hear that?
I heard
A little bit, yeah.
A bit of a high pitched.
I stopped it as fast as I could. Alright, so yeah, let's go through each of these. Okay. So the first one. Okay, so let's see if we can follow the rule that I said, which is you start off by taking your thumb and you point it in the direction of the magnetic field. So what direction is the magnetic field pointing for this north-south magnet here?
The right.
The right.
The right, yeah. So your thumb would start off by going like this. The next thing you do is you say, okay, so is the magnetic flux increasing or decreasing?
Decreasing.
Why is it decreasing?
It's moving
Magnet
further
going
away.
The magnet's going that way, so the flux has to be going down. You're getting, again, the strong part of the magnet is the tip right here, so there's a lot more magnetic field lines inside of these coils now than there would be when it moves away. So flux is going down. So when the flux goes down, you leave your thumb pointing in the same direction, and that's going to be the induced magnetic field direction. And then you just wrap your fingers around, and whatever way your fingers roll, that's the direction of the induced current. So what's the answer to the first one?
Beta A.
Really?
Maybe the loops from B to A.
Well, the question is, look. Express your answers in terms of the letter labels A to B, and it says, what is the direction of the induced current in the resistor?
Oh, that'd be A to B. They would be A to B.
Yeah, exactly. Okay, I see what you guys were saying with A to B to A, though. For all of these, it's always the resistor to make it more clear, but... Okay, so we know that it's going, basically from what we said, since it's curling this way, if I was to draw that on my picture right here, what that would look like, I'm just going to have to make this way bigger to actually draw on the pictures, though. Let's just move some of this stuff out of the way. Alright, so when we say we want to make it go like this, that means it has to be flowing down on this side. Basically down on all of these, right? I mean, that's the direction your fingers would curl. Down like that, right? And then it flows basically along the bottom here in this direction. So that's that's the direction of the induced current there. A to B. Okay, let's do part B. So this one's a little trickier because we have basically an electromagnet because we have a coil connected to a battery. When you throw the switch, for a very brief moment in time, there's going to be an increase in flux. What is the direction of the magnetic field produced by this electromagnet when we close the switch?
B to A.
No. I want to know the direction of the field.
Towards the right.
Towards the right.
Okay, and to figure that out, you look at the direction of the current because it flows from the positive side here, which means it goes up the back side and back around the front. So now we know that the current is flowing like this. Right? Which produces an external field that goes this way. Again, use your right hand to figure that out. So external magnetic field pointing to the right. That's going through our little U-shaped wire here. Is the magnetic flux increasing or decreasing in this case?
Increasing.
Increasing.
So what do we? So we point our thumb in the direction of the external magnetic field. We say because the flux is increasing, you flip the direction of your thumb, and that is going to be the direction of the induced magnetic field. So our induced magnetic field in this case is going to go the other way. I'm going to draw it up here. Okay, did everyone follow all those steps? Does anyone have any questions?
Made sense.
Mhm.
Yep.
So now, again, if the induced magnetic field's this way, now I curl my fingers again, and that's going to tell me the direction of the current. So in this case, that will be down this way, back up this way, and then from B to A, right?
Yeah.
Yep.
Okay, is this making sense to everyone?
Yeah.
Mm-hmm.
For those of you that aren't responding, I'm assuming that maybe it is, maybe it isn't. I don't know, but we'll keep doing more of these until it makes more sense. Okay. C. All right. Why don't you all tell me your answer before we do this one? What did you all get for part C? A to B or B to A?
I said A to B.
I also got A to B.
A to B as well. Okay. All right. So we have this current flowing to the left, and if we point our thumb in the direction of the current, our fingers will sweep in the direction of the magnetic field. So on the upper side up here, does the magnetic field point into the page or out of the page?
Into.
Yep. So
On the upper side, yeah.
I'm just going to draw it inside of our loop right here. So that's our external magnetic field. And that, again, that external magnetic field is coming from this wire right here. Now it says, we'll read the problem again. Part C says, what is the direction of the induced current in the resistor when the current decreases rapidly to 0? So if the current decreases to 0, the external magnetic field decreases to 0, which means we have a situation where the current is, the flux is decreasing. So when the flux is decreasing, you point your fingers in the direction of the external field, but then you just leave your fingers pointing in the same direction. And that's the direction of the induced field. So our induced field goes this way. And if I wrap my fingers around, if I point my thumb in the direction of that induced field and I wrap my fingers around, then I'm going to get that the induced current is going to go this way, this way, this way. Which is, as you all said, from
A to B.
A to B. Now, one thing that will almost always happen with these kind of scenarios, look at the current on the bottom down here. See how the current in the external wire is left, and the current in the bottom of this is also left?
Mm-hmm.
So that should always happen. If you have a decreasing decreasing current here, means the field needs to be the same, and the only way for it to be the same is to have the current go the same way, right? Same direction. At least on this one side. It's kind of complicated because the current's also flowing on the top too. But if we took this entire system and we moved it to the bottom, you'd have the same thing happen, where the current then across the side that's closest would point in the same direction as the current here. Just kind of a technical detail of something that happens. And again, if the current in the wire down on the bottom was increasing, the direction of the induced current would be the other way, according to Lenz's law. Okay.
Professor?
Yeah.
Could you go over part A one more time?
No problem. Okay, in part A, what we have is an external field. What was it? I was in green for external field, right? Our external field goes this way. So our induced fields, I think in part A it's moving away. That means that our induced field has to point in the same direction. So our induced field is this way. And if I put my thumb, then my fingers will basically curl around, which is telling me that the current is kind of coming across the front. And if the current's coming that way, then that means it's going to flow down this way, and back up this way. Does that make sense?
Yeah, it does. Thank you.
No problem. Okay, this stuff's kind of tricky, but you can figure it out. And again, like I said at the end of the day, it's not that big of a deal if you just get it wrong. I mean, it's 50-50. Okay, what are the other ones? I've got these ones here. Let's try these three. How much time do we have left? Plenty of time. Well, we're going to stop a little early today because I only gave you one break, which is kind of cruel. try these three. These ones may actually be simpler, but maybe I should have started with these ones. I was thinking these were trickier just because of the magnets. The magnets, I don't know. But the other one had magnets too, so what do I know? All right, try these ones. I'm gonna give you a little less time. We're gonna do 3 minutes for this one, if that's okay with y'all.
What does the first one say? I can't quite read it.
Oh, okay, I'll make this one bigger then. The other two are pretty self-explanatory, right?
Professor, for question 8, the magnet is going in, right?
8. Yes.
Yeah.
Yes. The lines behind it mean that it's moving away from those lines. Yeah, thank you. Good question. This is using cartoon
Indeed.
kind of graphics. Can you read it now?
Yeah.
Yeah, much better.
I'll still make it a little bit bigger.
Oh my god, 2020.
Now the other thing that can be kind of tricky about these is understanding what the front and the back is of these loops, which is probably why the other ones are a little easier to understand. But we're gonna basically call this the front side of this loop, and oh god, I have no idea what to do with question 8.
An optical illusion.
Yeah, it is an optical illusion, right? Just depending on like how your brain works, you're gonna see it either as this being the front or that being the front. Now you see these shadows here, right?
Mm-hmm.
I think those shadows imply that this is the front. Yeah?
Yeah, that's what I was going with that as well.
Okay, so the shadow side is the front side. So this is the front side of this one. This is the front side of this one. One thing I want to mention, by the way, too, is it's really, like, right now I am in, like, full, like, very, like, sad that we can't be in school mode because the demos for Lenz's Law are some of the best demos we have. Like, one thing that happens in this picture on the left over here that's really surprising is that when you push the magnet inside of the loop actually repels you, and then when you pull the magnet out, the loop is attracted to the magnet. So let's see if you can understand why that's the case as you solve this. Okay, so try these 3. I'll give you 3 minutes. Once you're good at doing these, they don't take any time, but I know that it will take you some time to look and understand. So I'll give you 3 minutes. Okay, how are y'all doing? Is that enough time?
Mm-hmm.
All right. Okay, so first problem. Okay, so on all of these, I'm just going to go through the same thing we did before. We're gonna write down the induced current direction based on the induced magnetic field direction. So let's keep going with that strategy. So we'll go. That's our external field in this problem, right? This is the direction of the external field in this problem. And let's see, in this problem, what direction is the current going to go? So this is the plus side of the battery, that's the negative side of the battery, so the current's going to flow around like this. So that's the current in the wire. And if the current flows that way, that means the external magnetic field at the center here is going to go into the page, right? Everybody agree?
Yep.
Yeah.
Okay, next thing to do then is to look at, is flux increasing, decreasing, whatever. So problem number 1, is flux increasing or decreasing? Or 8, question 8.
Increase.
Increasing.
Increasing, so we have to make the induced magnetic field go this way, right? Opposite.
Mm-hmm.
And then we just wrap our fingers around, and that means that the current has to flow like this, right? Up this way and back this way.
Yeah.
Okay.
Mm-hmm.
So let's. Okay, does anyone have any questions about that one?
Mhm.
Okay, now can you see what I was saying? That because when you push the magnet towards the loop, it makes the loop act like a magnet with the opposite polarity. You know what I mean? It makes the loop act like a magnet where this is the north end and this is the south end over here, right? As a result, when you push the magnet into the loop, the wire is repelled from it momentarily until the magnet gets inside of the loop and there's no more repulsion. And then when you pull the magnet out, the direction of the induced magnetic field flips, and then as the magnet is pulled out, the loop is attracted to the magnet. Does that make sense?
Mm-hmm.
Mhm.
Okay. It's a cool demo. I just, I don't have the setup to show you at home, but we have plenty of cool stuff like this that I could show you in the lab. Okay, let's go to this problem right here. We're trying to find the induced EMF in the blue loop right here. It says that determine the direction of the conventional current induced in the inner loop when the switch in the outer circuit is closed. So if we close the switch, what's going to happen to the induced... what's going to happen to the external magnetic field?
It'll increase.
Increases. So that means that we need to make our induced magnetic field point the other way. Out, right? Which means that our current basically has to be opposite the external current, right? So it has to go this way and this way, which is kind of consistent with what I was telling you in the last problem, right? It has to be if the current is suddenly produced in a circle like this, then the current on the inside has to be opposite that. And then the same thing would be true when I undo the switch, the direction of the induced EMF is going to be the opposite. Another thing to point out here, by the way, is that after the switch has been closed for some time, what's going on in the blue loop then? If I close the switch and let some time pass, what's going to happen with the induced EMF in this in the blue loop?
When I just
flip the
go
current.
back to 0. Yeah.
It goes to 0. It doesn't flip it, it goes to 0. Because a steady state magnetic field, right? A steady state magnetic field will not induce currents unless you move the loop, Does that make sense?
Wouldn't
Yeah.
the current eventually decrease?
No. Well, if the battery dies or something, maybe.
Yeah. Oh.
Is that what you're thinking of?
Yeah, that's what I was thinking of.
Yeah. Okay. Well, yeah, but I mean, you took the long time part of what I said very literally. I understand. Sorry, I meant if the switch has been closed for a few seconds, because it only takes like a nanosecond for the current to reach maximum. So yeah, so in this case, this induced EMF is only going to happen for just a second, like not even a second, less than a second, like a nanosecond. Okay, what about question 4? So question 4 pretty much is the same as question 8, right? It's just you flipped the direction of your magnet. And what I also want to talk about is what happens after the magnet gets past this point. So there's our external magnetic field, right? And what's happening to the flux through this loop? Is it increasing or decreasing?
Increasing.
Increase.
Okay, so we know that we need to make the external magnetic field, the induced magnetic field go down. Which means that to make that work, you have to have a current that flows this way, right?
Yep.
That's it. Now, what would happen after this passes, like after the magnet gets passed, so that we're at the situation where here's our loop, same loop, right? But now the magnet's down here. Now what direction is the induced current?
Wouldn't it flip directions?
Yeah, it has to, right? So now the flux is decreasing. So because the flux is decreasing, and by the way, the magnet's moving this way, motion. So now the induced field is this way, which means that your direction of your current has to be opposite what it was before. Like that, right?
Mm-hmm.
Now this leads to something that's really interesting. Suppose that instead of using a ring right here, I use a tube. Okay? So I take a metallic tube. It does not have to be magnetic, just needs to be a metallic tube. So I take a tube like this. I think you could do this at home if you happen to have a little toy magnet sitting around. Because all you need is just a metal pipe. If you have like some kind of metal pipe sitting around. I don't know if it's something you might have, but I don't know. Where I grew up, my dad had a lot of pipes for some reason. I don't know. But if you take a metal pipe, okay, and you take a magnet, here, let's make this a different color. So I can make the magnet red. So then we take a magnet and we put the north end of the magnet like this. It doesn't actually matter which end you put down. It makes no difference at all. I put the north end of the magnet like this and the south end of the magnet like this, and I drop the magnet through. Okay. Something kind of interesting happens. So again, look at the connection in this picture right here between the induced magnetic fields and the external magnetic fields. Can you see that they're opposite to each other? I mean, they're obviously opposite to each other. It's part of the way we set it up. But when we get to this picture, now what's their relationship? They're the same direction, right?
Mm-hmm.
So to drive this point home more, because I can use these little arrows like this to represent the fields, I can do the opposite as well. I can say, well, because this loop has an induced magnetic field that points down like that, that's basically like having a bar magnet here, right? Where the north end of the magnet is down here, and the south end of the magnet's up here, right? So the upper magnet is basically, think about this, it's repelled. The magnet itself is repelled by the loop, right? You know what I mean? This is like taking the south end of a magnet and the south end of a magnet and trying to push them together. It's going to be repelled, right? They're going to push off each other. They don't, you know what I mean?
Mm-hmm.
And then when we get to this picture down here, well, because the magnetic field's this way, this is like having the north end and the south end together, right? Where the north end is here, right? And the south end is here. So now look, this is north to south. So now this magnet is attracted to the loop after it passes through it. Isn't that interesting? So on the way down, because the flux was increasing, the magnet is repelled by the loop, but on the way, once it passes the loop, it's attracted to the loop, right? So think about what happens as a magnet now falls through a metal pipe, which the metal pipe can be thought of as a series of a bunch of different loops, right? It's like a bunch of different loops, right? And as the magnet falls through, it is going to be repelled by the induced current that's placed in these loops, okay? There's going to be an induced current as it falls. Let's get this the right way. It's this way, right? This is the direction of the induced current as it's falling. but then when it goes past, that direction flips, right? So the effect of this is that if you drop a magnet through a metal pipe like this, it will actually fall slower than the rate of gravity, because there's going to be another magnetic force that is always acting upwards on it, pretty much. Right? Think about that. It's always going up, right? I left that part out, but when the magnet is on the top side, it's repelled by the loop, which means what's the direction of the force on the magnet? It's up, right?
Up.
And then here, once it passes the loop, it's attracted to the loop, so what's the direction of the force on the magnet?
Up.
It's also up, right? So as the magnet moves down, it always feels some kind of upward magnetic force. And check this out, because we know that the rate at which the flux changes affects the size of the induced EMF, right? That means the rate at which it falls controls how big these magnetic forces are. So, you're going to reach an equilibrium where the rate at which it's falling produces a magnetic force upwards that is exactly balanced out by its weight, which goes downwards. So as this thing falls, it's going to fall basically at a kind of terminal velocity, because FB ends up being equal to mg. Okay? It basically falls such that this is true. It's an equilibrium as it falls. Constant velocity. It falls with a constant speed. Right? Because the magnetic force ends up being equal to the weight, which this leads to what I call terminal speed. Right? This is the same thing that happens for a parachuter, or sorry, not a parachuter, a skydiver, right? The drag force is proportional to your speed. So when you fall, when you're skydiving, when you're falling down, you speed up, you speed up, you speed up, you eventually reach terminal speed, because there's a balance where the rate at which you're falling produces a drag force that's equal to your weight. And so that's how you reach a terminal speed, right? The exact same thing happens here with magnetism, because the rate at which the magnet falls, according to Faraday's law, controls the size of the magnetism that it produces and the currents that it produces. And the bigger those currents are, the bigger the magnetic force is going to be. So there's obviously a balance is going to be reached. It just happens a lot faster. This thing reaches terminal velocity almost instantly when it reaches the tube. Like, the moment it gets inside the tube, it just starts to... It's really strange to even see. I wish I could show this to you. I can't show it to you. It is really strange to see something falling with a terminal speed. We are so accustomed to things just falling, right? To just watching objects that just fall. Like, that's what we're used to seeing. When you see an object that's moving with a terminal speed like this, it looks like it's floating. You know, it's doing something that is very foreign to our experience. And you can watch it. You can look inside the tube, and you can watch the magnet just slowly floats down to the bottom. It is very, very surprising. Very surprising result. Now, I want you to think about Faraday's law. Okay, I'll stop for a second. Do you have any questions about what I just kind of tried to explain there? Does that make sense?
Good. I do have a question about...
Look. Cam actually put a video on here.
Mm-hmm. I know that.
Yeah, I was about to say, I saw a YouTube video a while ago with this person who was melting metal with a copper magnet. Like, they just put it inside and the magnet just starts floating.
Yeah, it looks like that's the one he linked. Here, well, you can all see it. It's right
Nah,
here.
it's a different one.
Oh, it is, okay. Yeah, so, yeah, this is cool. Here.
Yeah, that's one of the neat ones.
Yeah, just like that. It's like it's floating, right? You don't have to spin it. He's spinning it to make it fall straight. It's pretty cool, though. And it doesn't matter what direction the magnet's oriented, either. It doesn't matter at all, because the effect, like, the pipe will just basically react to whatever the magnet's doing, you know? If the magnet flips, if it's flipping as it's falling, the direction of these currents are just going to be kind of oscillating, but they'll always basically be pointing in just the right direction to, you know, counterbalance the external magnetic field, because that's Lenz's law. That's how Lenz's law works. It's always got to be opposite. Melt metal with magnets. Let's watch this one, too. This sounds like something we should watch.
I know that one.
Let's see what this one's all about. A little longer. I've seen this one. So, does it tell you what is happening? So there's clearly some kind of wire Or this wire has some current in it, I guess, right? What's gonna melt? Is it the tube that's gonna melt, or the
metal inside.
one inside? Yeah, okay. And I'm assuming this is
We can
because
skip ahead.
the wire is has an alternating current inside of it, right?
And that's what I was gonna think. I was thinking, is it an alternating current? So like, I mean, something's heating it up. Like, so the electron's got to be like jiggling.
Is it already kind of like deformed? Yeah, it's hot. You can see that it's
Yeah.
red hot now. Look at that. That's crazy. It's interesting as it becomes more like liquid that it just starts to form into this like top kind of thing, and it's just like, whew, that's really neat.
Whoa.
So cool.
It's really, really cool.
It's a conservation of like angular momentum.
Yeah.
So,
Looks like a light bulb now.
Yeah, it really
Yeah.
does. Doesn't look like much else is gonna happen here. Wait, something happened there. Yeah, I guess he's gonna turn it off. It's gonna splat. Or does it just lose? All right, who speaks Russian? Because that's really neat. I like that.
That was just basically liquid in air.
Yeah, just like suspended through the magnetic field. That's wild. That's really cool. So I wanted to like connect all this back to conservation of energy before we leave. What time is it? Yeah, we really should stop. So just like think about what's happening here, right? And imagine that Lenz's law was reversed. You know? Imagine that Lenz's law was reversed. If the direction of the induced EMF was the same as the change in flux, then you could use this object as a gun, because it would actually, instead of having a magnetic force that points opposite the direction of the weight, they would actually point in the same direction. And because the magnetic force is dependent upon velocity, the faster the object moves, the bigger the field that it would produce in the pipe, which would then make the magnetic force bigger. And the magnetic force would grow exponentially over time then, right? Does that make sense? So what you could do is you could basically just drop something inside of here, and you could take the pipe and you could like aim it, and it would fire, you know, at a very fast rate. You could fire the magnet out of the pipe.
Close the pipe in a loop.
You could do that too. But can you see how that would violate energy conservation?
yeah.
Right? It just would, because it wouldn't make any sense that you would just be getting energy for free. And so that's why I say that Lenz's law is really a consequence of energy conservation, really, at the end of the day. It's like magnetic field conservation or something like that. I don't know.
I do have a question though about like one of the diagrams,
Okay.
the middle one. There's like a plus, so it's the battery, the plus, and then there's like the big bar, and then the minuses, the small bar, right?
Yeah.
But like in the last problem, I think it's the opposite.
Yeah, that got me confused as well in
That got me
at the beginning.
confused.
Oh, this is... Why did they do this?
Yeah.
So this is probably a typo.
Okay.
I just
Okay, cool.
I mean,
I was
if
like,
you
what was that?
if you look at your homework, the bottom picture down here is the one that's more consistent.
Okay.
Gotcha.
This is coming from a different textbook, but I'm just going to assume that's a typo. I didn't notice that. I'm glad you all noticed that. That's a good point, though. I apologize for the confusion. Huh. Okay. Okay, we need to stop. That's two very long like sections of lecture today, but I'll stop recording.